This question is a AC question. Basically, we're going to analyze the sine wave equation for the source, shall we say, that's given. Now, if we have this equation, it represents a voltage source, which is described by 75 times sine of 628t. Now, before we make a sketch, we will talk about what that equation means. And if we have 75 times sine of 628t, the unit is volts. Remember that that equation follows the basic format of V peak, which represents the amplitude, times sine of omega t, where omega t represents an angle in radians, whereby omega is the angular velocity of the generator in radians per second. Time is in seconds, and so that gives us a overall unit of radians, which is an angle in radians. However, omega is still the angular velocity of the generator. Now, for part A, we are asked to determine the amplitude of the voltage. Well, the amplitude of the voltage is the peak value of the sine wave, and so V peak equals 75 volts. Now, part B asks us for the angular velocity. As we've said then, omega is the angular velocity in radians per second, and so we have 628 radians per second. Now, remember that in our unit circle, what we're saying is that 360 degrees is equal to 2 pi radians, and that's where the unit of radians comes from. So 2 pi radians equals 1 revolution around the circle. Okay. Now, the frequency of the voltage waveform, part C, omega, is equal to 2 pi times the frequency of the given voltage. Now, and so, to solve for frequency, we will say F is equal to omega divided by 2 pi. Here, omega is 628. And we divide that by 2 pi, or 6.28, and we'll come up with 100 hertz is the frequency of the voltage waveform. That means that it produces 100 cycles per second. Now, and so when we say that, we mean the generator, as it rotates, it produces 100 cycles of voltage per second. That is the frequency of the voltage waveform. Part D asks us for the period. The period is the time taken to produce 1 revolution of the voltage, or 1 cycle of the voltage. And so the period is represented by a capital T. It is 1 divided by the frequency. And so we have 1 divided by 100 hertz. And that gives us 0.01 seconds, or 10 milliseconds for the period. Now, before we can do part E, and so part E here is the instantaneous voltage after 2 milliseconds. And so before we do that, we should think about a sketch. Now, I know that it doesn't ask us to sketch the waveform until part J, but for part E, basically we have this. The amplitude of the waveform right here is 75 volts, and the period is 10 milliseconds. That means that this point right here is half the period, 5 milliseconds. And so for part E, the instantaneous voltage after 2, remember the peak here occurs at half of 5, 2.5. So we are looking at 2 milliseconds, approximately there. And so this is the instantaneous value. At that instant would be a voltage represented by somewhere close to 75, between 50 and 75, I think. And so in order for us to do the calculation, we should consider the equation V is equal to 75 times sine of 628t. Now remember, t is the time along this axis here, which is time in seconds. And so if t is 2 milliseconds, that is 0.002 seconds, and we want to put that in this equation. Now the idea is that, remember that here this is omega, the unit is radians per second, and so the overall unit is volts, but for the sine function, radians per second times second gives us an angle in radians inside the brackets. And so basically what we're saying is that V will be equal to 75 volts multiplied by the sine of 628 times 0.002. Remember, this is an angle in radians. We have 75 volts multiplied by the sine of, when we multiply 628 radians per second by 0.002 seconds, we'll come up with 1.256. The unit is radians. That is an angle in radians. In order to determine the value of the sine function at that angle, remember your calculator must be in radian mode. And so everybody's calculator can be changed from degree mode to something called gradients to radian mode. Put your calculator in radian mode, take the sine then of the angle, 1.256 radians. You should be able to come up with 0.95086. Now that says that at 2 milliseconds, the voltage is about 95% of the peak value. Well, if you think about the graph we drew, pretty well close to 75. And so our calculation shows that the voltage at 2 milliseconds is equal to 71.3 volts. At a time t equals 2 milliseconds. Now, part F asks us for the instantaneous voltage at 120 degrees. Well, remember that if our axis here can be in time, can be an angle in radians, can be an angle in degrees. So if it's an angle in degrees, it means that a full cycle is represented by 360 degrees. A half cycle, 180 degrees. The peak at 90 degrees. So 120 degrees, about here. We're looking for the instantaneous value approximately at that point. Part F then says that we are looking for a voltage which corresponds to 75 times the sine of 120 degrees. So now, in order to do this, you have to put your calculator back in degree mode, and we have to evaluate the sine function for 120 degrees. If you do that, you should come up with 0.8 0.8660. And so the voltage then will correspond to 75 volts times 0.866, and that comes out to be 64.95 volts. And that is valid for theta equals 120 degrees. Now, part G asks us to evaluate our instantaneous voltage equation for a time of 50 volts. Now, if we go back again now to the simple sketch that we've made, when we get there, we will say that if this is 75 volts represented by the peak, then 50 volts probably occurs here somewhere. We want the time taken to reach 50 volts in what we refer to here as the first cycle. So where this is considered 0, this time right here. And so we're going to find that time by saying that the voltage equals 50 volts. And so therefore 50 volts equals 75 times the sine of, and we want to put our calculator back into radian mode now and use 628T. So the 75 will go to the denominator over here, and so we have 50 over 75 equals the sine of 628T. And so 50 divided by 75, 0.667 equals the sine of 628T. Now, in order to get t out of the brackets here, or out of the sine function, we wish to take the arc sine, or the inverse sine, of both sides of this equation. And if we do that, sine to the minus 1 of 0.667 is equal to sine to the minus 1 of sine 628T. Now, if we do it this way, what you'll find is that sine cancels sine here. And so what we're really saying is that the inverse sine of 0.667 is equal to 628T. Well, remember, T is in seconds. And so now, on your calculator, in radian mode, the inverse sine of 0.667 should be equal to 0.7297. And that is equal to 628T, where again, T is in seconds. Now, when we do this, we're going to take the 628, put it in the denominator over there. So T is equal to 0.7297 divided by 628. And so when we do that, 1.162 times 10 to the negative 3, and the unit is seconds. Remember that the 10 to the negative 3 is milli, and so what that means is time is equal to 1.162 milliseconds at 50 volts for the first time in the first cycle. And that kind of agrees with I think what we sketched on the graph above, right here, when we looked at this time, right, between the 1 and the 0 and the 2 that we had there. So that's not bad estimation on the graph. Remember, our graph not to scale very good there. So now this is a long question. If I scrolls back down here now, we are ready to look at part H, and for part H we were asked to find the angle in degrees at which the voltage reaches negative 25 volts in the first cycle. So I think what I'll do is I'll basically sketch this again now, and we're looking at this here, and our peak value is 75 volts. Now, and so if our axis is an angle in degrees, remember that 180 degrees occurs at halfway through. 360 degrees is the full cycle. And so if we are looking at the angle where we reach -25, remember that this would be -75. So let's say -25 volts is here. We're looking at an angle right here, somewhere between 180 and 270, let's say. Okay, so our calculation should say that the voltage is -25 volts. So -25 equals 75 times sine of theta. And so -25 over 75 equals the sine of theta. And so -25 over 75 is -0.333 equals the sine of theta. And so again, in order to get theta out of the sine function, we would need to take the arc sine of both sides. Now, if we want an angle in degrees, we need to put our calculator back into degree mode. Now, it's very important to switch your calculator from degree mode to radian mode to degree mode when you're doing these calculations. Have to have the calculator in the proper mode. So back to degree mode. We have the inverse sine of -0.333 is equal to the inverse sine of sine theta. And again, this means that the inverse sine of -0.333, which you can calculate, and it should come up as -19.5 degrees, and that should be then equal to theta, an angle in degrees, which tells us that V was -25 volts. Now, we have come up with -19.5 degrees, and so if we think about trig now, you have to realize that that does not agree with the little graph that we drew. However, the calculator has been designed to produce an angle in the area -180 degrees is less than theta is less than +180 degrees. And we said on this graph that our angle should be between 180 and 360. But our problem is that that value doesn't fit in the agreed range that the calculator is going to give us. And so what that means is that our angle will be 19.5 degrees away from this point of 180. So the correct angle that we're looking for will be 180 degrees plus 19.5 degrees, and we are looking for an angle of 199.5 degrees equals theta. Now that is out of our agreed range, but agrees with our graph. And so if you check on the calculator, both of these angles will give us a voltage of -25 volts, and you can check that. The math is easy to verify. Okay, one part left. Part I then asks us now to find 2 times that the voltage reaches -37 volts in the first cycle. And so what I'm going to do is I'm going to start by sketching that voltage waveform again. And so the voltage waveform looks something like this. We have right here 75 volts. Down on the bottom, -75 volts. And so in the first cycle, negative 37, we want this time, let's label it as T1. We'd also like this time, label it as T2. So now we want to go back and analyze our voltage equation for in order to find these two times. And so again, if we know that the period for the waveform is 10 milliseconds and the time for half the period is 5 milliseconds, the negative peak occurs at 7.5 milliseconds. We can assume that perhaps T1 approximately 6 milliseconds and that T2 would be approximately 9 milliseconds. And so if we start our calculation with that understanding, then we should be able to confirm the values and get an accurate answer from our calculations. And so if we think about our equation, remember that we're saying here that V equals negative 37 volts, and that V was equal to 75 times the sine of 628 T volts. And so if we consider as negative 37 equals 75 times the sine of 628 T, we have negative 37 over 75 equals the sine of 628 T. Negative 37 divided by 75 will give us negative 0.4933. The inverse sine of that value will equal 628T. Remember, when we took the inverse sine of 628T, we came up with 628T. So, if we agree that the calculator must go back to radian mode, then we evaluate the inverse sine, negative 0.4933, we will come up with negative 0.5159, and that is equal to 628T. And so T is equal to negative 0.5159 divided by 628. And that gives us negative 8.215 times 10 to the negative 4 seconds. And so we would like to make that negative 0.8215 times 10 to the negative 3 seconds, so that we can say this is a milli. And so we have negative 0. Let's say 82 milliseconds. Okay, so if you think about where that gets us on our sketch, this distance here, 0.8 milliseconds. This graph is supposed to be symmetrical. This distance right here, 0.8 milliseconds. And so we can conclude from that that the correct answer is T1 equals the period over 2 plus 0.82 milliseconds. And remember, 5.82 milliseconds for T1, because half the period we agreed was 5 milliseconds. Then likewise, T2 will be equal to the period subtract the 0.82 milliseconds. And so remember, we had 10 for the period, and so 10 subtract 0.82 says that the second time that we are looking for on our graph, 9.18 milliseconds. And so back to our graph, we have T1 here, 5.82 milliseconds, T2, 9.18 milliseconds. Now, that's a long question. I'm sorry it's taken so long. It's 25 minutes, but there's a lot of math in that question. The last part of the question was part J, and it asked us to sketch the waveform and to include the period and the amplitude. And so we can say that here is our waveform, and remember then the period here 10 milliseconds, the peak value at 75 if this is volts. Now I have a sketch that I can bring in. We'll show you the sketch. However, that might overwrite the mat. However, remember, if you want us to have a closer look at the mat, rewind the video or of course play it again. Now, we have then this graph right here, which is to scale now. It shows that the period 10 milliseconds, shows the half period at 5, shows that the period agrees with 360 degrees, shows us the positive amplitude at 75 volts, shows us the negative amplitude at negative 75 volts. Remember that the pure sine wave is symmetrical and looks very much like this one.